This lecture explains the material in the last part of section 2.2 in the book. This section is entitled Earth's Axis Wobbles. Tops wobble. The motion is decoupled into precession and nutation. Precession is a change in the orientation of the rotational axis of a rotating body. It is the slow movement of the axis of a spinning body around another axis due to a torque, such as a gravitational influence, acting to change the direction of the first axis. It is seen as a circle slowly traced out by the pull of the spinning top. Nutation is a periodic variation in the inclination of the axis of the rotating object. In astronomy, it is the periodic oscillation of the Earth's axis that causes the precession of the poles to follow a wavy rather than a circular pattern. The learning goals of this video are to understand what axial precession is, to predict where the north celestial pole will point for a given year due to the precession of the poles, to predict where the vernal equinox will point for a given year due to the precession of the equinoxes, to understand the causes of axial precession, and to learn about Milankovich cycles. First, we'll consider the effects of axial precession. A full 360 degree of Earth's precession takes 25,771 years, which works out to be about 1 degree every 71.6 years. Our book uses a value of 26,000 years for axial precession period, which yields about 72 degrees per Figure 2.12 shows the path of the Earth's spin axis sweeping out every 26,000 years. The location of the North Celestial Pole slowly drifts. Currently, the North Celestial Pole is very near the bright star Polaris. This is the star at the end of the handle of the Little Dipper. The left picture shows the South Celestial Pole for different years. The picture on the right shows the North Celestial Pole. Polaris has not always been and will not always be the North Star. Around 3000 BC, when the pyramids of Egypt were built, Thuban in the constellation Draco was the North Star. During the first millennium BC, the Roman era Ch02 of the constellation Ursa Minor was the North Star, and in about 12,000 years, Vega, the constellation Lyra, will be the North Star. What star will Earth's axis point to 12,000 years from now? That would be Vega. Which star was the North Star 5,000 years ago? That's Thuban. What star will be the North Star in the year 8000? That's Aldebaran. This picture shows another picture of precession, the precession of the vernal equinox point. The ecliptic is the path the sun travels on the celestial sphere. It lies in the plane of the Earth's orbit around the sun. Recall figure 2.9, which shows that as the Earth orbits the sun, different constellations on the plane of the ecliptic show up in the night sky. This image is not a star chart. It is a convenient depiction of the constellations of the ecliptic plane. The path the sun makes projected onto the celestial sphere is called the ecliptic. The constellations along this path are currently called the zodiac constellations. Although, as we will see later in this lecture, Ophiuchus and perhaps Orion should probably be added now due to the precession of the equinoxes. They are not part of the traditional zodiac constellations. Here's how Earth's orbit is oriented today. The constellation patterns are used only here to represent the region of the sky the sun is in on different days of the year. Winter in the northern hemisphere is when the Earth's spin axis is pointed away from the sun and it has a snowflake marker. The Earth moves counterclockwise in its orbit around the sun, as seen from the North Pole looking down. The markers show where the winter and summer solstices are and where the vernal and autumnal equinoxes are. On the vernal equinox, the sun's right ascension is very, very close to a star in Pisces called Omega Piscium. This star is also close to the celestial equator. On the vernal equinox, the sun is in the constellation Pisces. In Greek mythology, Aphrodite and Eros escaped the monster Typhon by leaping into the sea and transforming themselves into fish. In order not to lose each other, they tied themselves together with a rope. The Romans adopted that Greek legend, with Venus and Cupid acting as the counterparts for Aphrodite and Eros. The knot of the rope is marked by Alpha Piscium, also known as Aurisha, which means the cord in Arabic. Omega Piscium has a right ascension very close to 0 degrees. It is conveniently close right now to the celestial equator, being about 6 degrees above it. Omega Piscium is a very useful star for orienting a telescope that has tracking capabilities. The origin of the equatorial coordinate system, which is the right ascension and declination of the celestial sphere, is called the first point of Aries. That may sound a bit strange since we just saw it is in Pisces, but when the system was developed and precession was recognized back in around 120 BC, the sun was in Aries on the vernal equinox. The vernal equinox is called the first point of Aries because that is where it was when Hipparchus cataloged the stars and described the motions of the sun and planets. The vernal equinox is close to the star Omega Piscium. The vernal equinox is currently in Pisces, and it will next enter the constellation Aquarius in 2700 AD. Here's roughly Earth's orbit and spin axis orientation around 60 BC. Notice the tilt of the Earth is oriented differently due to precession. On winter solstice, the sun is in Capricorn. On the vernal equinox, the sun is in Aries. And on the summer solstice, the sun is in Cancer. And on the autumnal equinox, the sun is in Virgo. Today, on the vernal equinox, the sun is in Pisces. In around 2700 AD, the vernal equinox will shift to Aquarius. Let's take a look at how the vernal equinox shifts. Note the pole is also shifting, sweeping out a circle in the sky where on occasion a bright star coincides with the North Celestial Pole. The time in the upper right-hand corner of the screen is showing you what year it is, and the arrow is of course showing you where the vernal equinox is. The Earth's orbit is not a perfect circle, it is elliptical. This figure greatly exaggerates the view of the ellipse. At a scale of the view graph, the Earth's orbit appears to be circular, so a realistic picture would not suffice to show these concepts. Aphelion is when the planet is farthest from the sun, and perihelion is when it is closest. Right now, perihelion occurs during winter. The line between the aphelion point and the perihelion point is called the line of the apsides. The line of apsides precesses. The precession of the solar apsides was discovered in the 11th century by Islamic astronomer Abu Ishaq Ibrahim al-Zakali. He regarded the precession as being solar because his model of the solar system was based on the ancient Greek model, which had the Earth at the center of the sun, orbiting the Earth. Earth's apsidal precession is roughly 112,000 years for the ellipse to revolve once relative to the fixed stars. The Earth's polar axis, and hence the solstices, equinoxes, precess with a period of about 26,000 years relative to the fixed stars, the combined precession yields a period of 21,000 years for the ellipse to revolve once, due to the vernal equinox, that is, the perihelion, to return to the same date. Precession contributes to long-term climate variations of Earth, called the Milankovich cycles. This wiki figure illustrates the effects of precession on the northern hemisphere seasons relative to the perihelion and aphelion. Milankovich theory synthesizes the collective effects of changes in the Earth's movements upon its climate. Milankovich theorized that variations in eccentricity, axial tilt, and precession of the Earth's orbit determine climatic patterns on Earth. There are cyclical variations in the episodic nature of Earth's glacial periods. For the past couple million years, the Earth has experienced an ice age primarily driven by the change in Earth's orbit. These are known as the Milankovich cycles. For Milankovich, a Serbian astronomer mathematician who is credited for modeling them. There are three dominant Milankovich cycles. The first is Earth's orbital eccentricity. The shape of Earth's orbit fluctuates between being circular, that's 0% ellipticity, and more oval, being 5% ellipticity, on a cycle of about 100,000 years. The second Milankovich cycle is the axial tilt, or the obliquity of the ecliptic. The obliquity angle of Earth's equator to the plane of the ecliptic varies between 21.5 degrees to 24.5 degrees every 41,000 years. Today, the axial tilt is about 23.5 degrees. The third Milankovich cycle is precession. The precession has a periodicity of 26,000 years. First, let's consider differences in Earth's eccentricity. The shape of the Earth fluctuates between being circular, with 0% ellipticity, and more oval, being 5% ellipticity, on a cycle of about 100,000 years. Due to the change in Earth's distance from the Sun, the amount of energy received changes. Today's orbit results in only a 3% difference between aphelion, the farthest point, and perihelion, the closest point. Thus, in January, Earth receives 6% more light than in July. When the orbit is more elliptical, Earth receives variations of about 30% more perihelion than aphelion. Now let's consider the nutation. This is a slight rocking of Earth's axis caused by the changing positions of the Sun, the Moon, and all the other solar system bodies. The obliquity angle of Earth's equator to the plane of the ecliptic varies between 21.5 to 24.5 degrees every 41,000 years. Today, the axial tilt is about 23.5 degrees. Less tilt results in less of a seasonal effect, but a greater difference in the amount of light received by the polar and equatorial regions. One hypothesis is that the smaller the tilt will promote growth of ice sheets. Combined precession has a periodicity of about 21,000 years. This changes the location of the perihelion and the aphelion. Today, the perihelion is near the winter solstice. The precession results in more than just a sweep through the zodiac constellations. On the celestial sphere, the ecliptic path shifts and sometimes traces through different constellations. Presently, the Sun's path crosses the constellation Ophiuchus. The axis of the Earth's rotation varies within the Earth itself by about plus and minus 0.2 minutes. This motion is periodic or cyclic, with the Chandler period of 433 days and additional annular and irregular contributions. Motions of magma, deep sea currents, changing ocean salinity, winds, melting ice sheets, and even earthquakes all conspire to constantly change the distribution of mass within the Earth. The planet responds by continuously shifting its spin axis. This effect is known as polar motion. It is related to minor changes in the rate of rotation. The variations lead to the occasional introduction of a leap second in time. A leap second is a 1-second adjustment that is occasionally applied to Coordinated Universal Time, UTC, in order to keep its time of day close to the mean solar time. Without such a correction, time reckoned on Earth's rotation drifts away from the atomic time because of irregularities in the Earth's rate of rotation. Since the system of correction was implemented in 1972, 27 leap seconds have been inserted as of 2017. The last leap second was inserted December 31st, 2016 at hour 23, minute 59, and second 60 seconds UTC. In summary, Earth's precession is caused by gravitational pulls of the Moon and the Sun. The precession period is about 26,000 years. The effects are the North Star changes as the rotational axis traces out a circle on the celestial sphere. The location of the equinoxes precesses through the zodiacal constellations. Precessional motion has been related to long-term cycles of climate change called the Milankovich cycles.